Thank you, Walid. All right, so I'm Marjon de Vos. I work at the Laboratory of Genetics, but also at the Laboratory of Phytopathology, as the phytopathologists know, because they see me very often running around in the lab. So when I see the world, when I view the world, I see connections everywhere. So whether it is in my Facebook friends or my Twitter friends and colleagues all over the world, or in ecosystems or in evolution. And in evolution, you've probably heard of, Sir Roy talked about it before, survival of the fittest. This is a very known term. So when we have a genotype on one axis, so the certain genetic content and the fitness on the other axis, and a population would start evolving, you would increase in fitness. So one mutation would increase in fitness, another mutation, and so on. But of course, evolution doesn't go along a straight line. So you could ask, what is the possibility space of this evolution? Well, it might look something like this. So actually, it's super multidimensional, but for our visualization purposes, it's condensed into a surface. And then you can see peaks and valleys. And I just told you that evolution can only go upwards. So if you would start off with a population that is at the basin of a peak, it would actually, when it would evolve, it would go to the top of that peak. But then it gets stuck, because I just told you, evolution cannot go down. So what then? There is no innovation possible and evolution is constrained. However, if you would move into another environment, then it might well be that this whole possibility space of evolution suddenly looks different. And actually what was first was the top of a peak is now again the basin of attraction of another peak, and you can again move towards the top of another fitness peak. So this is how evolution can keep innovating. So for evolution, the environment is very important. So the environment. So there are many environments all over the world. And they're actually in all of these environments, they're all different ecosystems. And actually not just everywhere, we are also walking ecosystems. Because actually, we are covered in bacteria. And these bacteria, they sit at different locations of our body, inside and outside. And at these specific locations, they all actually form ecosystems. You could also see that infections are actually also such an ecosystem. So I study urinary tract infections. I study them in the lab, in an in vitro system. And for urinary tract infections, mostly women are infected of younger age. And when women are infected, they're mostly infected with actually one species, mostly E. coli. However, for elderly patients, these are more often infected with a whole community of bacteria, with different species of bacteria. So then I wonder, do these different species of bacteria interact? So are there ecological interactions between these urinary tract infection ecosystems? And you can measure those interactions in certain ways. So here you see them on the surface. And I've put two different bacteria on this surface. And when they get closer together, you see they start interacting. For positive interaction, in the lowest picture, you see some bacteria colonies. They become larger when they interact with another species. Or for the top, they actually become smaller if they interact with another species. So that's a negative effect. I also measure these interactions in liquid medium, artificial urine medium. And when I do that, I actually also can see many, many interactions. So every dot there is one interaction of one species with another species. And then you can see red and blue. And red is a positive interaction, which means that actually the bacteria help each other. And blue means that it's a negative interaction, that the bacteria compete with each other, or even worse, they may even fight each other. So you can also use that information to model these interactions, because I have measured the growth rate, I have measured the population size, I've measured the interaction on this growth rate, and I've measured the interaction on this population size. So when you do that, you can actually make a prediction about the ecosystem stability. So how stable are these communities of bacteria in people? So for instance, these are 4 bacteria of which one person was infected with. And if we then model these interactions, we see that it doesn't matter with what population size you start off with, you will actually always converge to the same level. So you can also imagine that if you would treat this infection with one antibiotic, however, it would not be able to eradicate all these different species, then you will actually converge back to the same ecosystem. And you will not be able to eradicate this infection. And normally, urinary tract infections are treated with antibiotics. And you all know, and you've heard before, that actually there's this rise of antibiotic resistance. When bacteria become resistant to antibiotics, they're not susceptible anymore, and they're not killed by these antibiotics, and infections cannot be treated anymore. So I actually wonder, do these bacterial interactions, do they have an effect on the tolerance or the susceptibility of these bacteria on antibiotics? So then I've measured again many of these interactions, and then you see, luckily, if you look at the change in effect of those, you see, luckily, there's a peak in the middle at 1, which means that if there are interactions, most of the effective dose is not changed. However, you also see that that this distribution is skewed to the right-hand side, which actually means that there are many positive interactions on antibiotic tolerance, which means that bacteria become less susceptible to antibiotics when they are grown together with another bacterium. Luckily, there are also negative interactions, and that means that actually that bacteria will become more susceptible to antibiotic when they are grown with another bacterium. So you can see this as 2 scenarios other than when bacteria are grown in isolation. So you have, let's say, you look at one bacterium, and this one bacterium is grown together with bacterium B. Bacterium A is grown together with bacterium B. And this bacterium B has a positive effect on the growth of bacterium A. You can also look at another scenario in which bacterium C has a negative effect on the growth of bacterium A. So what would then happen if you would add antibiotics? Well, since bacteria C has a negative effect, it makes the bacteria more susceptible, this infection will be earlier cleared. However, since bacteria B has a positive effect on the other bacterium, it will actually take a longer time before this infection is cleared. It will make it more difficult to treat such infections. And then all of this, Arthur already said, I look at also the evolution of antibiotic resistance. So do these interactions also affect the evolution of antibiotic resistance in these particular bacteria that I study in the lab? So and for that, I look at certain bacteria, and these bacteria are special. Luckily, they're not in all urinary tract infections, but in some. And these bacteria, they can actually crawl over a surface. So not all bacteria can do it. Normally, when you put bacteria on an agar surface, they start to grow a little bit, but then they stop. These bacteria are special. They can swarm over a whole surface. And actually, these bacteria, they're also responsible for kidney infections, because they start off in the bladder, and then they crawl up in the kidneys, and then they make an infection there, and they're actually also responsible for kidney stones. But all right, so I put these particular bacteria on a plate of agar, so on a surface. And then my question is, if I would precondition that surface with the exudates of other bacteria, will that affect their evolution of antibiotic resistance on this plate? So first you see the bacteria at the 0. The 0 means there's no antibiotic present. And then you see it becoming darker and darker, and it's becoming darker because there are more antibiotics present. So it's an increasing concentration of antibiotic. So now I'll put these bacteria on the plate, they will start growing, and then we'll see how fast they can swarm across this whole surface. It's a little movie, and it starts with day 1. So on day 1, they're already grown on this plate, and they are stuck, and they cannot move to the next level. On day 2, the building was closed, but all of a sudden, overnight, they have got many mutations, and they actually can swarm over the first level. On day 3, they actually got a super huge mutation that actually, boom, goes to the next level. And actually, on day 4, it's a little bit difficult to see because they actually are everywhere right now, but they have crossed this whole plate. So only in 4 days, these bacteria could cross this whole surface. So now we're going to look at another of these movies, but now it's conditioned, now the surface is conditioned by another bacterium. So again, we start off with day 1. The bacteria are sitting there, they're growing, they're dividing, but they cannot go to the next level. On day 2, they're sitting, they have grown a bit, but they still cannot move to this next level. On day 3, the same. So this one takes a little bit more time. On day 4, bam, you see small mutations happening, and they start swarming over the plate. Day 5, they start to swarm over the plate, albeit slower. Day 6, they got the 1 mutation, the next level. Day 7, okay, they just continue. Day 8, I was off, I took a day off. And then on day 9, actually, they spread, well, until the second highest level. So they weren't, in 9 days, we were not able to cross this plate. But as you can see, there's a black line, and actually this is when my surface collapsed, so I had to stop the experiment. But what you see, actually, is that these bacteria, so there are multiple replicates here. They don't all show exactly the same pattern, but there is a speed up and this slow down. And these are still preliminary experiments, but don't try this at home. So what I would like to say is that these preliminary experiments tell me that there's likely an effect on the evolution of antibiotic resistance based on interactions with different bacteria. And if you would actually compare this to the control, in which this surface was not conditioned by other bacteria, then it would actually be in the middle. So one bacterium actually speeds up the evolution, and it seems that one bacterium actually slows down the evolution on this plate. That brings me to the conclusions. I think that polymicrobial infections are actually an ecosystem, and not just a bunch of isolated bacteria, that we should look at in isolation. And currently, we're actually looking at these bacteria in isolation. Because these affect the ecosystem stability, the interactions affect the antibiotic tolerance, but I think they also affect the evolution of antibiotic resistance. And then with the knowledge that we gain by this research, we could actually invent new interventions based on this ecosystem knowledge that for which we might actually need less antibiotics, and bacteria become less resistant. And we can use those for further infections that we cannot treat on an ecosystem level. So acknowledgements, all people over the world, also in Wageningen, thank you very much. And thank you for listening.